right, so we have studied all the methods tests to check convergence of the series or divergence of series. So now we are ready to understand power series. Okay, and power series just technically just a special series, right? But they are in a certain form. A so-called power series will be in the following form. Oops, what is that? Where's this from? Oh, forget it. All right, the power series is a series in the following form. You start from 0, an, let's use a Cn, yeah, coefficient. Cn x minus a to the n. Okay. This is just x is some variable. Okay. The reason we want the motivation to study power series is when we're trying to solve a differential equation, and we are not able to solve it, but we probably cannot find an elementary function for the solution, but maybe we can express the solution as a power series. Okay. So if it is convergent, then you get a number depends on x. So therefore you get a function. Okay. So if this power series is convergent for some x, then you get a function depend on x, right? So this is a power series. If let's say okay, if it is convergent for x in some interval I, this could be open or closed, then we get a function, okay, on I. Okay, the function f, so f of x is defined to be the limit okay, so we have, yeah, conversely, a function on interval can be expressed as a power series, okay? But not every function can be expressed as a power function, first of all. But usually those are called good functions. They are those good functions that may not necessarily be expressed as an elementary function. Okay. So we have a, yeah, so we're given special series, we call it power series if it's written in that form, Cn times x minus a to the n. Okay. And if it is convergent for x in some interval, then we get a function of f on that interval, and which is given by this formula. Okay. So my first question is how to determine the interval for x, right? You know, for x in that interval, so so that this power series is convergent. So this is a question: how to determine x for which the series is convergent. Okay. Well, there is an important theorem. Mathematicians already find out, but it's not, I'm not going to give a proof, but it's get some ideas. So the theorem says that given a power series, okay, then we find out there's always the interval in which the power series is convergent will be very special interval. It will be symmetric, some kind of symmetric about A, okay? So the theorem says that there is a number R, okay? This number could be 0, finite, positive finite, okay? Or positive infinite, okay? That's only two of them, okay? Such that when the series is convergent for X in the interval A minus R and A plus R. Okay. That's the first thing. Yeah, it's a symmetric. Second, the series is divergent for X outside this interval. Okay, for X outside the closed interval, outside I should say A minus R, A plus R, okay? But we don't know the boundary, okay? We're not sure. Yeah, we don't know. Actually, the series must be absolute convergent on, yeah. So you can also add absolute convergent. Okay. Then you have to check the end points. Sometimes at the end points it's absolute convergent, sometimes just condition convergent, sometimes divergent. Okay. Okay. At the third point, at X equals A plus minus R, the series, okay, might be absolute convergent or divergent, or condition convergent or divergent. Okay, so we don't know. Okay, so you have to case by case to determine. Depends on the coefficient. Okay, so because you are going to consider this series plus minus R to the power n, so you have to really have to check this case when X minus A equals 1, right? So it could be usually could be alternating series. Okay. Now, how to find such R? Okay, how to find such R? We use the ratio test of rotor test in general. Okay, because it involves the n's power, right? X minus A to the n. So the question is how to find R. Okay, this is called the radius of convergence. Okay. Yeah. So the way we do is we find that in the following way. Take the limit and absolute value of Cn, X minus A. Okay, right? And to the power n, you can use nth root. Okay, then you will get then here's X minus A. So the determine, yeah, how to determine by A. So if this one has a limit, okay, if this one has a limit, then clearly it is as absolute convergent. Yeah, it is absolute convergent if the nth root of Cn, the limit, times it's less than 1, right? From here you can determine R. Okay, so in other words, R is going to be one of the limit of nth root of the absolute value. Right? Yeah, you divide move it to, so I going to be that. Then you can also look at, yeah, it's, it's divergent, then this is greater than 1, right? So it is divergent. You see that it's divergent if this is greater than 1, okay? So that means if x minus a is greater than 1 of that, okay? So that is the reason R should be equal to the 1 of the limit as n approaches, assuming the limit exists. Sometimes the limit doesn't exist, but be careful. Okay, so this is where we calculate, find the R, okay? And you can also use the ratio test. The ratio test is going to be Cn plus 1 here, x minus a to the n plus 1, divided by Cn, x minus a to the power n, right? After you simplify it, and here's x minus a, and you end up with the same inequality, right? So clearly, when this is less than 1, it is convergent. It is convergent, or even absolute convergent, if that is going to be x minus a is going to be less than 1 over. Okay, otherwise it's divergent. Okay, so this is how do we find the radius of the convergence. Okay. All right, so we got this brief idea, and let's do some exercise. Okay. So actually just use a ratio test, root test, right? So let's look at the following one. We are familiar with this power series. It's a very special power series. Okay. When it's convergent, I already know that. It's convergent when if and only if absolute x is less than 1. But let's use the idea how to do it, right? Use this idea. So we view as a general series, okay? Then an is xn, right? So we use a ratio test, use a root test. Okay? And I find out this is just equal to absolute x. Okay. So now clearly it is a convergent, absolute convergent if absolute x is less than 1, and divergent when absolute x is greater than 1. But how about, anyway, so I is going to be 1 in this case. Radius convergence 1. It's surprised, you know, the interval for which x is for x in the interval, the series is convergent. Actually, such x values form a interval symmetric about the origin. All right, so this I is a radius convergence. How about the endpoint? So you get an interval, right? And here's 0, this is 1, this is negative. So for x inside this interval, it is absolute convergent. Outside this interval, it's divergent. How about the endpoint? We look at the endpoints at x equals 1. It is 1. It's a divergent. Okay. And the same is true for negative 1. Right? So this is divergent. I cannot say negative infinity. Divergent. All right. In fact, okay. In fact, you have this geometric series is going to be 1 over 1 minus x. It's convergent. Not only convergent to 1 over 1 minus x for x less than 1. Okay? So let's understand this identity. So the left-hand side is a power series. I know it's convergent for x for the absolute x less than 1, and it's divergent for absolute x is greater than 1. And at the end, 2 endpoints, it's also divergent. But inside this interval, it's convergent to some function. Actually, the function is 1 over 1 minus x. Right. But look, when you look at the right-hand side, this 1 over 1 minus x is defined for all x except for 1, right? So they are equal only under this condition. Surprise there. So that function 1 over 1 minus x cannot be expressed as power series, well, by one single power series. Okay? It is going to be, yeah, only on this interval they match. Only on this interval they match. Okay. Yeah. In other words, if you are given function 1 over 1 minus x, only for x, absolute x less than 1, it can be written as this type of power function. Okay. All right, so now let's look at some examples. This is the problem number 4. In most of cases, the power series just x, power x to a certain power, okay? The third root of n, okay? Find the radius of convergence and the interval of convergence. The interval of convergence is just the largest possible interval for in which the power series is convergent. Okay. Okay, how do you do that? First of all, you determine the value of R, right? So just go ahead, you know, to use apply the ratio test or root test, doesn't matter in this case. Just use the ratio test. Okay, that's an plus 1. Okay, I just want to know when. Okay, when this can be, yeah, the limit should exist. Okay, so that is going to be to get a negative sign. Absolute of x. Okay, then you simplify it. You will get okay. And the limit is going to be just x. So clearly, when it's going to be convergent, right? So it is absolutely convergent if x, absolute x is less than 1. And it is divergent if absolute x is greater than 1. So from here, you already know the radius convergence. I is going to 1. My next question is, how about the end point? Is it convergent or divergent? So we look at the end point, x equals positive. When x equals positive 1, you get the series right? And clearly it's convergent. It's convergent. Why? By the alternating series test. Yeah, in this case, Bn equals the third root of n, it's decreasing to 0. Okay? Yeah, we just make a simple comment. You don't need to give all the details in that. It's clear. Okay? At x equals -1, the series becomes just positive 1 in the numerator. And this is divergent, okay, by the P series test. P equals 1/3, which is this one. Okay, then. So now, for what x, the power series convergent, for x between -1 and positive 1, but including positive 1. Okay, so the power series, so the power series, the series convergent if and only if x is between -1 and positive 1, okay? So the interval convergence from -1 to positive 1, including positive 1. All right, so interval convergence is that, including positive 1. All right, so the next problem. Let's consider let's consider this. Okay. Okay, clearly this is a convergent when x equals 0, right? I want to find the radius convergence. So we just go ahead to use the root test, not the ratio test, root test. Okay, ratio test doesn't work. Okay, the load test is going to be, you take n out, this is n absolute x, okay? And look at this limit. This is going to be convergent to infinity if x is not equal to 0, okay? Otherwise, it's 0, n times 0 is any 0. So what does that mean? This is greater than 1, so it is always divergent. Okay, so this is a divergent. Okay. All right, so never be convergent, okay, except for x equals 0. Okay, so that implies, yeah, this is an A, okay? So that means the series is divergent except for x equals 0. Right? So the radius of convergence 0. The interval of convergence is 0, just 1 point. Okay. That's the extreme case. You know, when you do some mix, do something, right? So yes, there's so many uncertainty there. Then you look at the extreme cases. Okay, if that happens, what I'm gonna do, right? Okay, so we're here, this is an extreme case. Okay, the radius convergence is gonna be 0. It's divergent for any non-zero x. Okay, so the next problem. Okay, clearly it has a radius. Its radius is going to be 1/2. I can tell them. All right. How to do that? There's no n factorial. I can use a ratio test. I can use a root test. Doesn't matter. Okay. So this is an, right? So we look at the ratio test. That's going to be 2 to the n plus 1, n plus 1 square, and x to the n plus 1. Right, so simplified, right? Then this will be 2, and n plus 1 over n square, and absolute x. So the limit is going to be 2 times absolute x. As n approaches infinity. Then what you get? Then by the ratio test, right? By the ratio test, you can tell that it is convergent if x is less than 1/2. Divergent if absolute x is greater than 1/2. Okay. But what happens when absolute x is equal to 1/2? But from here, you already know that the radius of convergence is going to be 1/2. Okay. But how about the end point? Okay. You already have the interval here, it's 0. It's positive 1/2, negative 1/2, right? So how about the end point? Right. So you look at the end points case by case. You have to check, right? When x equals positive 1/2, then you have the series. I think plus minus is enough. Yeah, here. So then you got 2 to the n squared, right? You look at this, right? So this is the nth term. So this is n. I look at the absolute n. Absolute n is going to the n squared absolute x to the n, but absolute x is 1/2. So after combine this n squared, it goes to infinity. So that means it's divergent because the nth term is does not approach 0. Okay, so this implies it is divergent by the nth term test. Okay. All right, let's do the next one. So the interval convergence is clear right now, just the open interval from -1/2 to positive. Right. So you can say the interval of convergence is positive, negative positive, right? Does not include the endpoints. How about number 14? Yeah, number 14. I should say that the interval of these pulses, the radius of convergence of this pulse series is going to be infinity. Okay, how do you see that? Now this time you have to use the ratio test because there's n factorial, okay? So you have look at n plus 1 divided by n, because the nth root of n factorial cannot be determined. So now you have okay. Simplifying, you will get squared, x squared. So clearly it's going to be 0 as n approaches infinity. But this is always equal to less than 1, right? So what does that mean? This is always less than 1. So this doesn't matter which x you choose. Okay, this is always absolute convergent. Okay, for any x. Okay, so the radius of convergence is going to be infinity, and the interval of convergence from negative to positive infinity. Okay, this is called interval of convergence. Right. That's just because there's always convergence. Okay, let's look at slightly different problem. Oh, this is power series. All right, so we do the same. Should I use ratio test? Should I use load test? I think doesn't matter. You have to use, let's use the ratio test. Okay, if I don't see n factorial, so you can use a row test too. Okay, let's use the row test. No, it doesn't matter. Okay, this is a. So then you can get right. The only problem is the nth root of square root n. How to express it? The nth root of square root n is the square root nth root this nth root of n, and here x plus 6 over 8, and that limit is going to be 1. Right. So you have the limit. So then you can tell when it's convergent, when it's divergent from the limit, right? So the limit tells you, yeah, it is absolutely convergent if x plus 6 divided by 8 is less than 1. So in other words, x plus 6 is less than 8. So 8 will be the radius convergence. Right? And it is divergent if absolute x plus 6 divided by 8 is greater than 1. Okay? So what happens when absolute x plus 6 is going to be 8? When the absolute x plus 6 is going to be 8, what happens? Okay. That one I can combine it together. Okay. So the series is going to be square n over 8 to the power n x minus 6 to the n, right? So x plus 6 is going to be plus minus 8. Not like that. You have to negative sign that, okay? Depends on the value. Since the coefficient is square n. I should say it's plus minus 8 to the power n. Yeah, that makes sense. Anyway, you can look at just n, absolute value of n. X plus 6 is going to be 8. So it's going to be square n. And clearly, this is not going to be approaches 0 as n approaches infinity. So the series is divergent. So now it's clear that the interval convergence will be just open interval. Okay. Now let's write down the radius of convergence is 8. Interval of convergence is just equal to x plus 6. Is extremely less than 8. Okay. So the interval, yeah, that's it. X plus 6. Absolute value that's less than 8. So you can solve this in Cody, right? X plus, and x is less than 2, greater than negative 14. How about this problem? Here B is positive. Okay. I can tell that the radius of convergence is going to be 1 over V. The interval of convergence is going to be x minus a less than 1 over b greater than or equal to negative 1 over b. Okay. So that means x minus a could be negative 1 over b. Yeah. Yes, the reason is this is going to be divergent, but this is convergent. Okay. So when x minus a equals negative 1 over b, you end up with this integral. Why 1 over natural log n is divergent? The sum. Who can tell me? Why 1 over natural log n is divergent? Can you see quickly why it is true? The reason is 1 over n is divergent. And the natural log of 1 over n is bigger than 1 over n. So you can use a comparison test, okay? So think about that. Natural log of n is smaller than n for large n. 1 over natural log n is greater than 1 over n, right? Right, the last idea. And then sigma of n equals 2. And which is infinity. Of course, the other one is infinity, right? Now, why this is true? Well, double check that. Why this is true? I think it's true. Natural of x is always less than x. Right? When natural of x grows, then when x equals 1, this is already less than. Yeah, it's always true. Natural of x is less than x. Okay. Yeah, proof. How to prove? Okay, you take a difference, right? X minus natural log X, that's called the f of x, right? Okay, f prime x is going to be 1 minus 1 of x, right? And which is going to be x minus 1 positive. Good. Okay. So positive is this means the function is increasing. Okay. So increasing means f of x is greater than f of 1. What is x? So not only that, even you can do better. Okay, even you can show that this is a lesson. You can even prove that this is going to be less than x minus 1. Okay, so this implies natural log x is less than x minus 1 for if x equals 1. Okay, now we proved that, right? So let's go back to the problem. Why is the radius of convergence of 1 of b? The radius of convergence is 1 of the b is, let's go back to this problem. Right. This is n, an, right? You have to use the ratio test, okay? Not root test, because the square root of n's root of natural log n, we don't know, right? So this one, we really don't know. Right? So I cannot use that. But when you use a ratio test, be careful. The original statement is there is absolute value on that. Don't just put an plus 1 over an. Right? So that's going to be natural log n plus 1, b to the n plus 1, absolute x minus a to the n plus 1. And this is b2. Okay. Okay, let's simplify it. After simplifying, I get a b absolute of x with no n. Right. Then I have a but this approach is what? Right, so this approach is b absolute of x minus a. So now it's clear when it's convergent, when it's divergent. Okay. If bx minus a is less than 1. Right? If it's divergent, if the okay, so that's why its radius convergence is 1. It's going to be 1 or b. All right. Okay, let's try another string problem. Okay, let's look at this. N factor x to to the n, 1, 2, 1, 3, 5, all the way to the 2n minus 1. Find the radius convergence and the interval of convergence. So let's try to find the radius convergence first. But did you see n factorial? So that means you cannot use a root test. You only use a ratio test, okay? You can simplify it. Because this is an an, okay? So n plus 1 over n, don't forget to put the absolute value there, okay? So this is going to be n plus 1 factorial x absolute of x to the n plus 1. It's 1, 3, 5, all the way to the 2n minus 1. That's not enough. It's 2 n plus 1 minus 1. Okay. Then I don't have enough space. Then upside down, I get 1, 3, 5, all the way to 2n minus 1. N factorial absolute x to the power n. Okay. So now you can simplify n plus 1 factorial over n factorial is n plus 1. And then absolute x. And you have another term. Okay. So now the limit is going to be absolute x divided by 2. That's it. Okay. So clearly, when it's convergent, when it's divergent, right? So it is absolute convergent if absolute x is less than 2. Divergent if absolute x is greater than 2. All right, so the radius of convergence is 2, but what happens at the end points? That is pretty tricky problem, right? Yeah. How about x equals 2, right? When x equals 2, this nth term is going to be n factorial 2 to the n, right? No, this is a okay. So now it's pretty strange. Because the limit is going to be, in this particular case, right, the limit of n root of n is going to be what? Does n approach 0 now? Okay. So if we put absolute value, right, then you can just look at absolute value. Okay. I think this does not approach 0, but it's harder to prove. Okay, it's harder to prove it. So the term in the middle, okay, it's going to be like that. 1, 2, 3, all the way to n factorial. 1 is actually 2 times 1 minus 1. 2 is 2 times 2 minus 1. 2 times 3 minus 1. There's 2 times n minus 1. Then you have a 2 to the power n. Okay. But then you realize that. When you realize that k over 2k minus 1, right? That's corresponding term. This is not an easy problem, yeah. You have to be very good in math. So you make some observation, and then you see that's greater than, you agree, then it disappears, k disappear. It's always greater than or equal to 1/2. Every term, vertical, okay, the two numbers. Okay, so that means this is a greater than 1/2 times 1/2 times 1/2 times 1/2, right? And times to the entire. After you simplify, this is going to be 1. So that term n, absolute of n, is always greater than 1. So it does not approach 0. It's not going to be 0. So that's why it's divergent. So it is divergent. The series is divergent. The power series is divergent for x. Absolute value x is going to 2. Okay. So the series is divergent for absolute value x equals 2. Okay. Then the interval convergence is going to be just -2 to positive. Okay. So that's it. That's not included endpoint.